Okay, so I'm just doing a video because it's a little easier for me to explain like visually than it is for me to just like try to figure out how to put it in a sentence. Hopefully it's helpful. Maybe it's not. I'm gonna frame it through the lens of like potentially it eventually being a resource for other people who might have a similar question, like notably within Winna. So I might explain some concepts that you're already pretty familiar with. I likely will. So feel free to kind of like skip through or fast forward. But hopefully it answers your question. Okay, cool. With that being said, the main question was basically what is the main reason that we subtract g from WACC in the denominator of the Gordon growth model when computing terminal value? So if we go to Gordon growth formula terminal value, you can go ahead and pull this one as much as this one. Okay. Okay, we can go ahead and pull that and paste it here. Oh, I already pasted it here. I was looking at it earlier. Okay. So, yeah, basically what I like to do here is basically pull it apart, make sure that I'm able to see different parts of the equation independently and kind of play with some of the inputs to better understand them. So here, I'm going to take the last year of unlevered free cash flow. So here, for full context, we have our DCF. DCF has 5 years historical, 5 years projected, and this is our final year, 2029, and we're taking the unlevered free cash flow of our final year. And so we're taking that, multiplying it by 1 plus our growth rate. That's going to give us this number right here. And then we're going to take our WACC and subtract our terminal growth rate. And so this right here would be our numerator. This would be our denominator. Awesome. So first, in terms of general understanding, I'm going to actually go ahead and do this first. Let's do terminal value. Then if we take this divided by this, it should give us, yeah, we can see it gives us our exact terminal value that we got when creating our model. Awesome. So with that being said, for full context in terms of understanding each of these numbers independently, so first you have the numerator. So the numerator is basically telling us what the forecasted cash flow would be in the next most year. So if we, for example, forecasted out 2030, we would get an unlevered free cash flow for that year of this sum right here, 188 and some change. And so that is basically all the numerator is. It is basically like year 6 of our forecast, right? So we have year 5, this is essentially year 6. Then we have the denominator. So the denominator is kind of like what I would view as a master discount rate in a sense. You could call it like the net present value decay rate. Um, I think I've heard other things, but basically what we're doing here is we're looking to see, okay, if we're going to grow these into perpetuity to get a terminal value, and just for kind of a refresher, the terminal value tells us, okay, if we are going to project our cash flows or our unlevered free cash flow out, not just for 2030, but for basically like into infinity years, how much would that add up to? Like taking each year into the future, adding that up. That'd be your terminal value, right? So since this is effectively our year 6, if we are going to grow our cash flow to a degree, it's kind of like a what rate should it be at question, right? And so you have two rates to grow or to shrink your cash flow, right? So you have, for example, growth rates, which drive cash flow all throughout your actual individual projections, and then you have your WACC, which shrinks it by discounting it based off of like what returns investors want or would expect, right? And so, with that being the case, you have to take both into account. So, basically, by doing that, you net them out, take the WACC, subtract it from the terminal growth rate. Your WACC needs to be greater than your terminal growth rate in order for the Gordon growth model to work. That's like a big key point. But that gives high level understanding of like what these numbers are, why they are the way they are. To get a little bit more in depth, I'd actually like to visualize this as a multiple. So, let me actually, yeah. So, I was playing around with this earlier. Oh, not super, but okay. So basically, like if I were to then visualize this, so let's do equals this, and then let's do um let's do 3 decimals. My decimals and my formatting is not going to be consistent. Just a heads up. Okay. All right. So basically, taking this, turning it into a multiple, right? We can see that 5.54, which is our denominator, is equivalent to around 18 years, right? And so you might ask yourself, well, why years? Because conceptually it makes it easier to understand what this number does. And so if I were to take this and multiply it by this, I would get my terminal value. So I'll explain why that is. Multiple, and then this would be, let's do this. Okay, so basically what this tells us is this, at this rate, right, it would take 18 years of this, like year 6 free cash flow to make up our terminal value. So essentially, what's being priced into our terminal value is 18 years worth of this amount of free cash flow, essentially, right? And so that can kind of contextualize this rate a little bit. Um, it's a little bit more complicated than that, but something that would help, I think, for me is to kind of I like to play around with the assumptions to understand like how numbers change, and like what that tells us about their relationship, right? So, for example, let's say that we had a higher WACC. Now we're taking into account way less years, and the reason for that is as we discount over uh at a higher multiple or a higher rate, you are going to hit what is basically zero faster. So, in order to contextualize that a little bit, there's something called like Zeno's paradox. And let's do yeah, dichotomy. Let's do that. So, for example, looking here, basically what Zeno's paradox tells us, it's like this like Greek philosopher guy, is that like if you keep cutting a distance in half forever, you will never quite finish the distance, but the total distance is finite. So you could cut this up into like infinitely smaller pieces, but the total distance is finite. Like it's absolute, it's one number, right? And so a way of kind of understanding this in terms of how you can apply the rationale to the DCF here. Let's take this image, which visualizes paradox square. I'm just gonna pull it over here. All right. Let's say we had like a value of 1 here and a value of 1 here. So you could tell me pretty easily based off of those values that the area is 1, right? Um, but oh, actually, I don't like this square. I want a different one. Give me this one. It's easier to read, sorry. Um, okay. All right. So, like I said, value of 1, oops, value of 1, value of 1, area of 1. But let's say you didn't know those values necessarily, and instead you basically took half and then continuously split it into smaller and smaller parts. So you took half of half, half of that, half of that half, half of that half, half of that half, so on into infinity essentially, right? What you're basically doing with terminal value and with Xenon, like Zeno's like paradox is you're taking 1/2, adding 1/4, 1/8, 1/16, and you could do this into infinity. But when you add all of these up, it would equal 1, right? And so similarly, for our purposes, what we're doing is we are forecasting free cash flow. So you have like, oops, that's really ugly. Let's do, uh, okay, like year. Oof, that's so bad. I'm so sorry. Okay, year 6, free cash flow. Year 7, year 8, year 9, and so on, right? And so what you're doing here is, let's say you have year 6 of, what did we have? 188.47, right? That's what we said we had for our year 6 forecast. So 188, right? I'm not going to do the decimals. And so basically what you'd have to do to get here is this number times n, right? And n would be like basically what we're doing here in terms of like times 1/2, times 1/2, times 1/2, times 1/2, times 1/2 into like an infinite sum, right? And so how we get this n would effectively be to calculate the retention rate. So the formula for the retention rate is pretty simple. So let's do like, let's call this like retention rate, right? And that's going to be 1 plus g over 1 plus r whack. Awesome. That's pretty messy. 1 plus r whack, r. So instead you do times r, and then you do that times r times r, in order to get each value. And you would then sum all of those up into infinity to get your terminal value. And this is unlevered. Or, yeah, I mean, it's basically unlevered. It's not fully unlevered, but it's basically unlevered. And so if I pull back up here and we were to essentially calculate the retention rate, right? Retention rate, we were to take, let's say, kind of like how I mentioned, we were doing equals 1 plus our growth rate. All right. Okay, cool. So we have a retention rate of 94.85. So that means like as we move on from year to year, we're retaining around 94.85 of what is basically the previous year's forecasted free cash flow, right? Okay. So let's actually build that out a little bit because I think it helps to see it visually. So let's go ahead and do, let's take these. And I'm going to do custom. Let's do a year. This is not standard formatting. I'm just doing this. Okay. This can be year five. What do we want? Year 5? Let's start with year. Yeah, let's start with year 5. And then this is forecasted, right? Because we forecasted that. And we have year 6, which is our denom. And then we have 7. And then we can just do. Cool. So year 5, we literally built this out. We have it right here. Year 6 is our numerator. I don't know why I said denom. Cool. And then basically for our year 7, we're going to do this times our retention rate, right? And so I'm going to go ahead and lock that and start pulling that over. And then from that, we want to see the shrink year over year. Let's do um okay. All right. So this is going to help us see this year doesn't have anything after it. The year over year shrink essentially. Wow. Okay. I'm actually gonna pop back up this. Awesome. And okay. So we can see here that our year-over-year shrink is a little bit closer to 5.15. I'll talk about why that is in a little bit, but that's kind of the visualization of the impact of this denominator. And the retention rate we computed independently of the denominator. And so the fact that we're still yielding like the correct values kind of illustrates how what drives the model is priced in to these two factors. Or what drives the model, I guess in this case, would be like what drives the forecast, right? Um, so the retention rate and everything like that is essentially kind of like algebraically priced in to like this more simplified Gordon growth model. And so what the denominator does is it kind of drives like the net shrink rate, or the net rate that like it's like basically discounting the present value. When I say present value, I don't mean like you don't need to do this step. It's basically discounting to the present value of like the final year. So 2029, as opposed to the present value of 2024, which is what you would actually do. And so eventually we're going to need to discount 2024, which is why we have this line item here. But that's independent of actually calculating terminal value. That's just discounting it afterwards. And so, yeah, that kind of gives a cleaner visualization, hopefully, of like how to think about the ratios, or at least like how I like to. Um, with that being said, basically I would say like, okay, the only thing that would stand out to me at this point is like, well, why is this number different than this number? And it's basically like 5.54 is like the true shrink rate that makes like infinity finite. So it's kind of taking it at like a larger picture, then it would yield something closer to this number. But since we're looking at it more year to year, and we're getting like this 5.15 due to like how like basically like the stuff compounds and the rounding compounds um in terms of like like basically like how the equation itself is structured. Um, but this is basically like the year to year decay, whereas this would be a bit more of like the bigger picture in a sense. And so part of what drives this is like you're discounting year 7 more than you're discounting year 6. So that's one thing to note. Um, but yeah, so this kind of shows like the underlying shrink rate before like you're really like considering things like timing and all those sorts of things. But yeah, both are basically telling the same story. One is looking at like maybe like 2 years, whereas this one is zooming out towards infinity, and hopefully that contextualizes um, how we actually go about deriving terminal value, what it actually looks like, visualized. And then this idea of like the denominator as a multiple, I think helps me a lot because I can start to think like, okay, like we're basically looking at like this value times this number, and that'll give us this. And as we start playing with, let's say we're growing at a higher rate, okay, well, you're gonna have a higher terminal value, right? So let's say we have like, we can't do 10 because then it'll be higher. Let's do like 6, right? Now, we're growing at this rate for way longer because it takes way longer for these numbers to hit 0, right? Because if we look, the value that we're discounting at is so much lower. So we're shrinking it by a smaller rate than before when we had 2. We were shrinking it by 5. And so that impacts like basically like how many years it takes. And the reason for this is like if we were to visualize this, right, as a line, this line is going to effectively just continue to get closer and closer to 0 and never actually hit 0, but like it materially looks like 0 because the values will just be so low. It's kind of like like looking into this little tiny corner over here, like it might as well be 0, for all intensive purposes. And so as we, let's say, increase this to 5, it's going to take way longer for that to hit 0 because you're starting at like a higher point. Um, or let's say conversely, this becomes more expensive, right? So the weighted average cost of capital increases. Now, we're going to die out in 5 years. We're only taking in 5 more years of growth, basically, to determine like value into infinity. And so this company's a little cooked if they got a terminal growth rate of 2 and a WACC of 20, right? Um, so that's basically how to think about that, and you kind of see like how the chart begins to shift. Um, yeah, we start kind of getting real close to 0 real quick, as opposed to let's say like our WACC here was like, let's not do 2, let's do like 2.5. It's like we got a while to go. You can look at the numbers over here. Okay, that's basically everything. Yeah, hopefully that contextualizes it. Definitely a fun topic, potentially. I don't know. Um, but yeah, let me know if you have any questions, and I hope it helped.